So this equilibrium constant, this is a way that we can quantify the concentrations of reactants and products at equilibrium. And if we look at our generic equation here, this is the formula for the equilibrium constant. So K, the capital K, we're going to have the product concentrations divided by the reactant concentrations. And each concentration is going to be raised to a power. That power is equal to the coefficient. With rate laws, we can't use the coefficients unless it's an elementary step. It's so tempting. Here, we get to use the coefficients. So the concentration of C raised to the power of its coefficient times the concentration of D, and then in the bottom, we have the reactants. I used to have, I remember getting confused, which one goes on top, reactants or products? And what helped me was to think of delta, right? Delta is change in, and it's always final minus initial. So this is kind of like that. It's the final products divided by the initial reactants. Do you want notes? So here, again, the brackets mean concentration in moles per liter. We have to be a little careful with our letters here. So a capital K that is not italicized is the abbreviation for Kelvin. Capital K that is italicized is a variable, and so that's the equilibrium constant. I will not try to trick you with that, but as far as I know, my slides are consistent in that. Okay, and that relationship is called the law of mass action. Did you have a question? Right. So in, printed stuff, a variable is italicized, and a constant or a unit abbreviation is not italicized. Yeah. You can get through life just fine without knowing that, but now you do. Okay, so we've got this reaction, 2A plus B in equilibrium with 3C. Which of these would be the correct equilibrium constant? D. Yep. So we've got the concentration of C cubed, products over reactants, and in the denominator with the concentration of A squared times the concentration of B. Any questions? So here's another chemical equation, N2O5 in equilibrium with NO2 and O2. So we can write the equilibrium constant expression for this. It's going to be the products, this one raised to the fourth power, times oxygen. We didn't write the coefficient 1 here. We don't have to write the coefficient 1 there, the power exponent there. And that's divided by N2O5 squared. Okay. The coefficients become the exponents. Write the equilibrium constant expression for the combustion of propane. Well, all we need is that balanced chemical equation. The equilibrium constant is going to equal products over reactants. So for products, we have CO2, and that has a coefficient of 3, so it has an exponent of 3. Then we have H2O, coefficient there is 4, so that's the exponent, divided by C3H8. That has an unwritten 1, and so we're going to give it an unwritten 1 here. And then we've got oxygen to the 5th power. Any questions? Hopefully you're thinking, well, this seems pretty simple. It is. I just want to make sure we're all on the same page, because if we're not seeing this, we're going to have trouble. We got to get this down. Okay, so the significance or the meaning of the equilibrium constant. If k is large, and by large we mean a lot bigger than 1. Not like 5, but maybe like 5 times 10 to the 20th power. I mean, we're talking really big. If k is large, that means that the numerator is bigger than the denominator, right? In order for k to be big, which tells us that the product concentration is greater than the reactant concentration. And that tells us that the equilibrium favors the products. It's going to go mostly to the right. Example, this might be 1.9 times 10 to the 19th power. Now, practically speaking, with an equilibrium constant that large, we would probably treat this reaction as if it was a complete reaction. So a lot of reactions will go to what is, practically speaking, complete reaction. It may be difficult to detect that there's any reactants left, but there actually are. I don't know that anything really goes all the way, because that would just be too nice, wouldn't it? Yeah, nothing's perfect. Any questions about that? Does that make sense? Yes?
A complete reaction is where the reactants are complete.
Yeah, complete reaction would be where all the reactants are gone. And pretty much never happens. Yeah. You can get really close. You can get close enough that you can't tell the difference, right? But never quite get there. If we have a small k, much less than 1, this is less than 1, 4.1 times 10 to the minus 31, really small. Well, that tells us if k is small, then the numerator must be small and the denominator must be big. So large reactant concentrations, low product concentrations. I think that is the best way to remember, well, k, it's a big number. Does that mean it goes to products or reactants? We should be able to answer that fairly quickly. I don't think memorizing it is a great idea. But you think, okay, big K means products over reactants. If it's a big number, we've got more products, less reactants, it favors the products. Small is the opposite, it favors the reactants. Okay? Important to note, that equilibrium constant says nothing about how fast it gets to equilibrium. It could take 1,000 years to get to equilibrium. It could take 2 seconds or a nanosecond. Says nothing about that. The rate is what we learned about in chapter 15, and we're just going to kind of set that aside and talk about equilibrium now. So this is just a summary. When K is very small, reverse reaction's favored, forward reaction doesn't happen much. When K is approximately equal to 1, and 10 might be considered approximately equal to 1 on this scale of plus 31, minus 31, neither direction is favored, and the reaction's about halfway. If K is much bigger than 1, the forward reaction is favored, and it essentially goes to completion. Again, we have colors on the slides which don't translate very well to your black and white printed slides. So you might want to circle or do something so that you can tell which ones are supposed to be red and which ones are supposed to be black. Make them different. I always think I should go back and, change that. I never remember. There's some things that life is just too short to waste time on. Anyway, so here we have this reaction, A in equilibrium with B. A is the red ones and B is the black ones. And we have this at 3 different temperatures. So the equilibrium constant, like the rate constant, can change with temperature. So we're asked, at which temperature is the equilibrium constant the largest? So large equilibrium constant, does that mean more products or more reactants? More products. So we're looking for the one that has the most black ones, right? So that's going to be C. Okay? Another conceptual question. Equilibrium constant for this reaction is 10. The reaction mixture initially contains 1.1 molar A and none of the product B. Which statement is true at equilibrium? This is a conceptual question. We're not supposed to have to do calculations. So the first one says, well, the reaction mixture is 1 molar A and 0.1 molar B. So that would mean that it's not going very far to the right, it's staying more to the reactant side. Or it's A is going to be smaller and B is going to be bigger, meaning that it goes more towards the products. Or the concentrations are going to be equal. Are the concentrations going to be equal? No. The only time they could possibly be equal is if the equilibrium constant was 1, and even then, depending on the stoichiometry of the thing, it might not be equal. So we can tell that this one's wrong. Well, the equilibrium constant is 10, which is, kind of in the middle there, but it's bigger than 1, right? So larger than 1, does that favor products or reactants? Products, right? So answer B, we've got more product than reactant. So that's the correct answer. That make sense? Well, what if you modify the chemical equation? I don't know if you remember from Chem 1A, Hess's law, and we were adding equations and steps, and then we were adding the changes in enthalpy, and we had some rules about how the heat of reaction changed if you messed with the equation. So this is similar, but different, of course. So let's think about this. So here we have A plus 2B in equilibrium with C. So we could write the expression for the forward equilibrium constant. C cubed over B squared. Whoops. Let's do A first. A times B squared. Easy enough. Here we've written the reaction in reverse. We put the products on the reactant side and the reactants on the product side. Well, we write the equilibrium constant according to how the equation is written, and so it's products over reactants times B squared, those are the products, divided by the reactants, which are now C. That make sense? What's the relationship between these two? They're inverses of each other, right? If you take this and upside down it, you get this one. So if you reverse the equation, you invert the equilibrium constant. With Hess's law, when we reverse the equation, we change delta H's sign. If it was negative, we made it positive because it was going the opposite way. Here, instead of changing the sign, we're changing the exponent. So we're making it a negative exponent, and so that's flipping it upside down. So this kind of correlates to the changes for delta H, except it's one mathematical step up. Instead of adding, subtracting, this is multiplying, dividing. If you multiply the coefficients by a factor, you raise the equilibrium constant to the same factor, With delta H, if you multiplied, you just multiply delta H. Here, you're going to use that coefficient or that factor, and you're going to raise it to a power. So again, let's write the equilibrium constant expression. So we have C cubed divided by A squared, not A squared, A times B squared. And over here, we would have C, but now this is 3 times some factor. So it would be 3n would be the power. Down here, A to the n power and B to the 2n power. That's a little harder to understand. Any questions about that? So we're not going to like multiply k by this number. That's what we did with delta H. But it's going to be raised to what the power of whatever that factor is. So that tells us that k prime is equal to the original equilibrium constant raised to the n power. If we add two equations, what did we do with the delta H's? We added them, right? Here, if you add equations, you're going to multiply the equilibrium constants. So if you're interested in all the math behind that, I'd be happy to explore it with you. I find it helpful just to think of it as a step up in function, right? So instead of adding or subtracting, we're multiplying, right? So let's look at this. So A is in equilibrium with 2B. This would be its equilibrium constant, B squared over A. Here's another equation, 2B in equilibrium with 3C. That would be C cubed over B squared. So if we add these two equations, we see that the two B's cancel out. I guess it's not 2B. And we'll call this K3. And we can write the expression for that. That's going to be C cubed over A. So I'm taking this and I'm just looking at this equation and writing out what this is. Now, what this statement is telling us is that K3 is equal to K1 times K2. So K1 times K2 is supposed to equal K3. Well, let's see if that's true. K1 is B squared over A. K2 is C cubed over B squared. And so B squared in the numerator and the denominator cancels out. C cubed over A. I'm not going to require you to demonstrate why this works. I'm showing it to you to just, help you believe me, and because some of you are interested in that. What you need to remember is that if you're adding these two equations, you take those and you multiply them. These are usually given to you as a number. It might be 5, and this might be 5 times 10 to the negative 3, or something like that. You just take those numbers and multiply them, and that's the new equilibrium constant. But this is why that works. Any questions? Skip something. Another conceptual problem. Again, reaction of A going to 2B. The equilibrium constant is 0.010. What is the equilibrium constant for the reaction B going to 1/2 of A? what we want to do here is we want to figure out how was this manipulated to give us that? What's the first thing you noticed? It's reversed. So it's reversed, and so then what do we need to do? Invert. And what else is different? The coefficients are different, right? So this has been divided by 2, and this has been divided by 2. So coefficients divided by 2. And that means the exponents are divided by 2. So if we're starting with 0.010, the first thing is to invert that, right? And what's the exponent on this? It's 1, and so to divide it by 2, it becomes 1/2. You could also write this as, okay, well, it was 0.010. Now to invert it, it's going to be to the -1. Divide that by 2 is to the -1/2. Okay? When you raise something to the 1/2 power, that's the same as taking the square root. So this is 1 over the square root of 0.01. When we go 1 over 0.01, the value gets bigger, right? And then the square root makes it smaller. So without using a calculator, what would we guess? It's probably 10. So this is, when we tip that over, we're going to get 100, and then the square root of that's going to be 10. And you can always do that on your calculator. 0.01 to the -1/2, 10. Any questions? Consider the following chemical equation: an equilibrium constant at 25 degrees Celsius. Why are they telling us the temperature? Do we need to use the temperature? We don't need to use the temperature in the calculation. It's just like with the rate law. This constant will change with temperature. So they're just being thorough and saying, this is the equilibrium constant at 25 degrees, and I'm asking about this thing also at 25. That's all we need to know. So say calculate the equilibrium constant for this one. And again, what we're going to do is we're going to look at, well, how was this equation changed to make this equation? Yeah, the coefficients were multiplied by 2, and it's reversed. Everybody see that okay? The COF2 became the products. So that means we're going to take that equilibrium constant and invert it, so to the -1 power. This is a 4, it used to be a 2. So then we're going to multiply the exponent by 2. So that's going to be 2.2 times 10 to the minus 10 to the 5 raised to the -2 power. We'll just stick with 2 sig figs here and get 2.1 times 10 to the minus 11. Question?
Why is it 5?
Yeah, thank you. I'll blame that on old eyes. Thank you very much. When I raise that to the second power, that's going to change this part. Did I do that wrong? So you're probably looking at that and saying, well, 2.2 to the second power squared, that's going to be 4 something, or 5 maybe. But then when we invert it, it changes. Yeah. So that's why it doesn't look like it makes sense. Because this part, oops, didn't mean to do that. This part would actually be 1 over 4.84. That's where that comes from. Any other questions? More practice. Predict the equilibrium constant for the first reaction given the equilibrium constants for the second and third. So, like with Hess's law, we want to look at these two equations and see how can we combine these to get that. There's different ways to do this. What I like to do with Hess's law is use a highlighter to help me keep track of all these different things. So I'm going to highlight that in green, and then I'm going to look at these other guys and find that same thing. Here it is in green. And maybe the carbon dioxide is going to be red, because there's CO and there's CO2. CO2 is over here. That's the only place. We'll make water blue, right? H2O. Where is the H2O? H2O is here. And then maybe yellow for hydrogen. So there's hydrogen, 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 and purple for carbon monoxide. That's an excuse to use your different colored pens, right? It also just makes it easier to see, especially if you have, dyslexia or anything like that. If you identify these with color, then it's going to make it easier to keep track of what's going on. So I'm trying to make this first equation out of the second two. So I'm going to look at this first equation and say, well, what's the first thing in it? Is carbon dioxide. So I need one of these equations that has carbon dioxide in it, and it needs to be reactant. Well, here we have carbon dioxide. It's a product. So that tells me I need to reverse that equation, right? Write it backwards. So CO2, I'm going to leave the state symbols off because they're all gases. Plus H2O in equilibrium with CO and H2O. So when I reverse the equation, what do I do to the equilibrium constant? I invert it. So here, this is K2 to the negative 1. 1.0 times 10 to the 5th raised to the negative 1 power. And I'm just going to finish color coding these, partly because, this is kind of fun. Blue, water, and carbon dioxide, and helium, hydrogen. Okay, so we got this guy taken care of. The next one, we want hydrogen. Well, we got hydrogen. It's great, but we need 3 hydrogens. So we already used this equation. We're not going to do anything with that. If we multiply this by 3, we're going to mess up the CO2, so we don't want to do that. So let's use the other equation. Oh, this has 2 H2s as reactants. If I add this equation in, then 2 plus 1 is going to be 3. So I'm just going to copy that one down as is. We're going to add the equations and multiply the equilibrium constants. So this is going to be equal to K3. We didn't do anything, did we? It just stayed the same. So this is 1.4 times 10 to the 7th. And again, let's highlight. So I've got 3H2, I've got CH3OH on the product side, I've got H2 on the product side. I think I'm done. So I added those together, and this equation matches that one. Good, that's what we're going for. Over here, this is, we'll take this number, 1 times 10 to the 5th. Yeah, it's a 5 this time. Helps to turn on the calculator, just saying. 1 times 10 to the 5th. I'm going to raise that to the negative 1 power. And I forgot to push one of the buttons. There we go. And then I'm going to multiply that by the other one, 1.4 times 10 to the 7. So my new K is 140. Anybody else get that? Is that the right answer? Just like that. Questions? Yes? Well, we can't say that K2 times K3 equals K1. Is that what you're saying?
No, I did the equation of K3 equals K1 times K2 to find for what K1 is.
But we have to have this negative 1 exponent in there. Yeah. That's a good idea, though.
So 140.
Yeah. I mean, you could say, well, look at, this is what I was doing to these guys. So then K1 is going to equal K2 to the negative 1 times K3. You can do that. Yeah. Any other questions? Right answer.